Hey everybody, I want to start by writing down a famous result about the sum of an infinite geometric series. So let's let f be the first term, and then we'll let fr be the second term. R stands for common ratio, and we'll go plus f r squared Okay, again, you get from one term to the other by just multiplying by r. Okay, then let's put the customary ellipsis. Okay, y'all, this is equal to, and it's fun little, it's not hard to prove this. And I do have to write down a few more things, but it's the first term in the numerator over 1 minus the common ratio. And this isn't very hard to prove if you look at the corresponding finite geometric series case. And also, folks, we do have to stipulate that R is trapped between minus 1 and 1. And you can write this way. Of course, this is absolutely equivalent to minus 1 less than R less than 1. Oops. Minus 1 less than R less than 1. So these two statements are equivalent. And it's very easy to believe something like this because the R's just get smaller and smaller and smaller as long as they are trapped between minus 1 and 1. Okay. Now, so we want to establish that this left-hand side is less than 34 over 35. And this is, I'm not going to try to prove this, but the big idea is to note that the finite geometric series of positive terms is always strictly less than the corresponding finite infinite geometric series. All right, if all the terms are positive and you have a finite number of them, that sum is going to be less than the infinite sum, of course. Okay, so here we go. Now, let's see, I hope I left that on the screen okay. Yeah, I think I did. Now, y'all notice what I've done right here. This object here, which actually is a base 7 representation of 0.54 repeated. But notice that what I did is I just rearranged right here. Okay, so that. Okay, so these are two finite geometric series. All right, and notice that 5 over 6 would be the first term. 5 over 6 would be the first term here, and 4 over 6 squared would be the first term for this one. Okay, and I didn't quite leave it on the screen for you, but I hopefully it's good enough. So, yeah, there we go. So this is the result. And I've done most of the arithmetic right here. Now let's see, this works out to, this part right here is equal to, and it's more useful just to leave this in the form of a common multiple, a common denominator, but not a least common denominator. So this is 34, the numerator combined up here is 34 over 36. Now notice the least common denominator is 18, but in my opinion, it's just a little bit easier to work with 36 because 36 is what's going on down here. So this is divided by 35 over 36. Okay, and then of course when you invert and multiply, you get that this is equal to 34 over 35. So a fairly cool way to do this if you recognize that it's just two finite geometric series. And again, y'all, I just started, here's the object we started with. I rearranged it this way. So this is a finite geometric series. This is a finite geometric series. This is the sum of the first finite geometric series. This is the sum of the second finite geometric series. when you do the algebra and the arithmetic on that, you end up with 34 over 35, which is what we set out to prove. Okay, this 34 over 35 right here. And we've done it. And just a side note, this is actually, this right here, you may recognize this, is 0.54. And I'll put bar, folks, or overline. I've heard this called overline lately, overline. But this just repeats, but this is base 7. Isn't that cool? So this is 0.54 repeated in base 7. Okay, and it's less than this number right here, 34 over 35. And we just proved it fairly quickly. I think another way to do this is maybe Cauchy-Schwarz, but you're left with a lot of arithmetic if you do Cauchy-Schwarz. I think a lot of arithmetic, you're having to deal with large exponents. You can probably simplify it okay, but this little result right here is powerful within this particular structure. So anyway, that's that. I think I got everything working. Thank you for viewing.